So let's suppose that you were working at a little candy store for your summer job and someone wanted to order exactly 1,000 jelly beans. Well, I doubt you'd like to spend your time actually counting out 1,000 jelly beans. So what's another way you might be able to measure them and count them out rather than individually one by one? Well, you know probably that we could do that by weighing them. Let's see how we would go about that. First, assume all the jelly beans have the same mass. So you'd have to weigh one of them and find the mass. Let's say we find the mass of one jelly bean to be 5 grams. If we want to count 1,000 jelly beans, we just calculate 1,000 beans times our conversion factor, 5 grams per one bean, right? Our beans cancel out and for units, and we have 5,000 grams, or that's the equivalent of 5 kilograms. We move the decimal place 1, 2, 3 to the left, and we have 5 kilograms. In reality, though, jelly beans are not identical. So let's say that we weigh 10 beans, and they each have these masses right here. Okay, I have them all written down right there in grams. We can count the beans by using the average mass. So this is a little review, and some of you who know this already, just bear with me. But the average, when we find average of something, we take the total sum divided by the number of items that we are adding together. So average mass will be the total mass of the beans divided by the number of beans. Down here we did this calculation. I added all the masses together on the numerator, and the denominator has 10 beans. Now, if we keep track of significant figures here, when I'm adding all these numbers up, the limiting factor, they all have the same one significant figure after the decimal point. So there's not really a limiting. They're all equal in the number of significant figures, and that there is one after the decimal point. So we can have one significant figure after the decimal point when we add them up. So our sum is 50.0. We have 10 beans. That's an exact value, so that does not affect our counting of significant figures. So our answer is actually 5.00 grams. Then to find out the mass of 1,000 beans, we actually will end up getting the same answer as we did when we assumed that all beans had identical mass. We're going to take the average, and it's going to be 5.00 grams times 1,000 beans. Our beans cancel out, and we end up with 5,000 grams. And the number of significant figures here is going to be limited by the number of significant figures in this measurement, 5.00. That has 3 significant figures, so we can have a 5.00 kilogram answer. So let's suppose that you want to get candy for your 2 little brothers, but they like different candy, 2 different kinds, and they must have equal numbers of the individual candies. So let's look at this problem. How are you going to do this quickly? Well, we know the average mass of a jelly bean, it was 5 grams. The average mass of the mint was 15 grams. We scoop jelly beans into a bag on a scale, and let's say it reads 500 grams. So let's look at the ratios of those. We have 15 grams to 5 grams. 15 grams representing the average mass of the mint, 5 grams representing the average mass of the jelly bean. That ratio is a 3. So 3 times 500 grams, which is the mass on the scale of our jelly bean, is going to give us 1,500 grams, and that was what would be what we'd need to weigh out for our mints into a second bag. 1,500 grams of the mints then would give us the equal number of mints as the number of jelly beans. So I hope you've just discovered a really important chemistry principle here. For 2 samples containing different components, jelly beans and mints, they're different components, both samples will contain the same number of components if the ratio of the sample masses is the same as the ratio of the masses of the individual components. So the ratio of the mass overall is going to be 1,500 grams to 500 grams, and the ratio of the individual components is 15 grams to 5 grams. Those are the same ratios. They're equal to 3 or 3 to 1. And so we know that both samples have the same number of individual components. So keeping this principle in mind, we can make some very quick and easy calculations using this idea. We'll just recall that our mass of the jelly bean is 5, mass of the mint is 15 grams. And let's say each sample contains 10 components. We want to have a bag that has 10 components of each. Well, we would just do dimensional analysis here. We have 10 jelly beans, and we're going to multiply by the conversion factor. 1 jelly bean is equal to 5 grams. And set that up so our jelly beans cancel out, and we get 50 grams of beans. So in 50 grams of beans, we'd have 10 jelly beans. How about the mints here? If we want 10 mints, we're going to multiply by the conversion factor here. Mints cancel out, and we have 150 grams of mints would be equal to 10 mints. What if we had each sample containing 100 components? How would we calculate the mass of that? 100 jelly beans times the conversion factor would be 500 grams of beans. 100 mints times its conversion factor, 1,500 grams of mints. In each case, the ratio is still 1 to 3. Now let's look at something other than candy. Let's look at atoms. Now if you look at this formula right here, we have this represents 1 carbon atom reacting with 1 molecule of oxygen to yield 1 molecule of CO2 or carbon dioxide. How many atoms are present in the pile of carbon atoms? Wow, that's a big question, right? We need to understand a couple of things first. We can measure the mass, right? We know that from what we looked at with jelly beans. We can measure the mass to find out the number of atoms, right? But we need to know our conversion factor. The mass of carbon happens to be 1.99 times 10 to the negative 23 grams. We can go ahead and just do that conversion right now. But we tend to use units, other units here. We're going to talk about atomic mass units, and you're familiar with that. 1 atomic mass unit in this case is 1.66 times 10 to the negative 24th grams. I didn't put my grams on there, but grams should be on there. Isotopes of carbon. We need to understand different isotopes of carbon. We have 3 different isotopes of them. Carbon, remember, always has 6 protons, but it has different masses, and we see it as a mass of 12, 13, and 14, the different masses of carbon for the different isotopes. Now remember, we can take the average, right? Any sample, one thing to remember, any sample of carbon contains a mixture of the isotopes, and those the mixture of isotopes, the percent of each type of isotope, is always going to be in the same proportion in any sample. So we can very confidently take the average atomic mass for carbon, and that happens to be 12.01 atomic mass units. And if you'll notice, by looking on the periodic table right now, you'll see that 12.01 is the mass that is written in the periodic table for carbon. It is the average mass of all of the different isotopes in their respective proportions. So if our pile of carbon atoms, let's say, here's our example problem, if it weighs 3.00 times 10 to the 20th atomic mass units, how many carbon atoms are present in this sample? So let's look at our conversion factor. 1 carbon atom is going to equal 12.01 atomic mass units, okay? And you can look on the periodic table very easily to find that conversion factor for each element. Now, how do we set this problem up? Let's start with what we know, 3.00 times 10 to the 20th atomic mass units. Write in our conversion factor with atomic mass units on the bottom so that they'll cancel out. 1 carbon atom equals 12.01 atomic mass units. And that's going to equal 2.5 times 10 to the 19th carbon atoms. Our atomic mass units cancel out, and we have the number of carbon atoms present in that sample. So you try. Calculate the number of copper atoms present in a sample that has a mass of 1,779.4 atomic mass units. You can pause the video, try that on your own, and see if you get the right answer. So the answer is 28.00 copper atoms. Here's how we do the problem. Here's our conversion factor. We start with our 1,779.4 atomic mass units of copper, and we multiply by the conversion factor. If you look on the periodic table, you see that 63.55 atomic mass units is the mass of one copper atom. Okay, and that equals 28.00 copper atoms. We're limited by 4 significant figures here, right? There are 4 sig figs. So here's another problem. Try to calculate the mass in atomic mass units for a sample of aluminum that contains 75 atoms. So here's the answer for that. Here's our conversion factor. 1 aluminum atom equals 26.98 atomic mass units. So let's start with 75 aluminum atoms. We're just doing this in reverse. Start with the number of atoms, multiply by our conversion factor, 26.98 atomic mass units per aluminum atom. The atoms cancel out, and we end up with 2,024 atomic mass units for the answer for our problem. So here are a few more problems to try. You can answer these on the next frame. Just go ahead and pause it, read through the problems, and see if you can get those right on the next frame. Here are the answers to the problems. Go ahead and make sure you answered all of those correctly, and if you did, then you are proficient at calculating these types of problems. And so you've passed off this section. So if you'd like to look at something more for advanced proficiency, just flip to the next frame. Advanced ideas, look up the isotopes and their percent abundance for your favorite element. Calculate the average mass for a given sample. Compare it to the mass on the periodic table. Perhaps create more complex problems of your own and any other ideas you have. I look forward to seeing you in class, and congratulations on learning this new concept.